Okay, folks, welcome back. This video is going to go over introducing another type of potential energy, which is the potential energy associated with a spring. So let's say we have a situation where we have a horizontal spring. So you don't need me to tell you that if you take a spring and you stretch it out, then the farther you try and stretch that spring, you might have noticed that the harder it is to continue stretching that spring. Or if you're going to compress the spring and make it smaller, the more you compress the spring inwards on itself, the harder it is to continue pressing it. But regardless, as you push the spring in to compress it, your hands are going to feel a force from the spring wanting to expand, going back outwards. And if you take the spring and you expand it, making it longer, your hands are gonna feel like something is pulling it back in. So the spring is trying to pull your hands back in. So if we make it longer, there's a force from the spring which is going back into the middle. So the spring is always a restoring force. So as we take our spring, we push it inwards. It's going to try and push back outwards. So a couple things we need to define with our kind of first little bullet point here. We have our unstretched spring, we have our compressed spring, and then we have our stretched spring. So the natural spring length, when it's uncompressed, this position that we mark at the end of that spring, that is our equilibrium position. So you might see that as X naught or D naught. A little zero there means initial. So this could be like our initial position in the X value in terms of how much our spring has been compressed or stretched, or our initial position just labeled as D. It doesn't matter. Now, when we compress the spring, we're pushing inwards on it. So there's an applied force on our spring, and the spring is wanting to expand. So the spring is going to try and push back outwards. So when we compress our spring, we're compressing it a distance D, which puts that location, the end of the spring, now at some final horizontal position. So we we compressed it from some initial X value to some final X value. Likewise, if we are going to stretch it, then we're pulling outwards on the spring. The spring is trying to come back to its natural length. So the spring is pulling you back in. So from our unstretched position, we're going to pull it to our stretched position. So still, this is xi equals 0. This will be x final equals some value equal to d in this case. So we have this restoring aspect of the spring. If the spring is elongated, it wants to go back into its natural length. If the spring is compressed, it wants to push back out to its natural length. It wants to restore itself to its natural length. So that's what we've got here. So first things first, spring thing number one is this relationship here. When we are going to push a spring inwards, it wants to push outwards. When we pull a spring outwards, it wants to pull back inwards. Spring thing number two, so the stiffer the spring, the stronger the spring, the harder it is to displace it from equilibrium. So the harder it is to get this compression or the stretching. So more and more of a force would be needed to actually make that happen. Okay, and that stiffness, that spring strength, we call the spring constant. So for a large spring constant, more force is required to stretch the spring, making it longer, or more force is required to compress the spring, making it shorter. This stiffness that we're talking about is called the spring constant. We use the variable K to describe that. So let's say we have different springs, and we're going to hang the same mass on top of at the end of our spring. So we have our unstretched spring length. This is our equilibrium position. If we put a 5 kilogram mass on our first spring and it only stretches the spring this amount, at this location, then the force is in place. Since we're not going up and down, we've got the spring supporting our mass upwards. We got gravity pulling the mass downwards, which is equal to mg. So these two forces would be equal to each other. Ditto up here, should have mentioned before. When we are compressing our spring and we're holding it there, if we're not accelerating anywhere, then this compression force is equal to the force of the spring going the opposite way. Or if we stretch our spring out and we hold it, then the force from the spring is equal to the force that we're using to stretch. Now, if we see that for the same mass, we're going to get a smaller stretch on one spring compared to the next spring. That means our smaller stretched spring has to be a stiffer spring. So we would have to include more mass on this one than 5 just to get it to continue stretching all the way down to the same position as our other one. So the relationship between force and this displacement, this stretching, this compressing, and the spring constant is this right here. So this is called Hooke's law, or the Hooke's law of elasticity. So this is the force from our spring we have our spring constant, the strength of the spring, the stiffness of the spring, and then we have much it's stretched or compressed in a particular direction. So again, it could be the y direction or the x direction. Please note though, most often you'll still see, even though for a situation like this where the spring is stretching vertically or compressing vertically, you'll probably still see these listed as x values. So our equilibrium position, x initial, will be our unstretched spring length, and then we would have our final stretched position. Those are just vertical values though. There you go, and our stretch and compression. So this negative here, this is there again to tell us that this is a restoring force. So this here is telling us that the spring wants to go back to no stretch. So again, if we pull the spring outwards, the spring pulls back inwards. If we push the spring inwards, the spring pushes back outwards. And that's what that negative is telling us. And that's how we use it. Now, how much work is required? We can't use our FD cosine theta formula for the work because the force is not constant, because as we try and stretch it more and more, it's going to require more and more force. It's a variable force. But we do get a graph that looks like this when we graph the force versus displacement. So we don't see a constant force, which would look like this, but we do see a varying force that is nice and linear, however. So the area of this curve will still, the area underneath this curve will still tell us the amount of work done to stretch or compress the spring, and that'll tell us how much energy is stored in there. So let's say that we look at the area here. It's a triangle, so 1/2 base times height. Base is distance, the height is the force, but the force is the spring constant times the distance. So we get 1/2 base times height. Okay, so our base is the force, which is just the absolute value of our spring constant times its stretch. We have, again, the stretch, so we get 1/2 K times our stretch squared for now the potential energy stored in a spring. So the work done to compress our spring. So let's say we have an object which is in motion, moving towards a horizontal spring like we have here. Okay, so just as finishing our kind of page, we have an object in motion this way. So it's going to come in, collide with our spring right here. It's going to start to compress our spring. If we're moving when we come in contact with a spring and we compress the spring is going to slow us down until we come to a stop after displacing the spring a certain amount this way. So the kinetic energy that we had when we were coming in contact with the spring has now been removed and stored as a different type of potential energy, just like when we're moving a ball vertically upwards or downwards through gravity. So we have kinetic energy stored as spring potential energy. And then when the spring unloads, it's going to push our box back to the right. It's going to send it flying off to the right, and we're going to gain all of our kinetic energy back. So we have now 2 types of potential energy we can use: gravitational potential energy and the potential energy associated with a spring that has been stretched or compressed. As always, if you have questions, please make sure you write them down and let me know. See you next time.